Okay, so hello and welcome. I have another problem to work on here. This one's going to be minimum genetic mutation on Leetcode, and I am kind of tired. You have to forgive me. Kind of like, I want to say something like my thoughts have been racing lately. I've just been kind of all over the place. Actually, let me back up. I want to. A couple things. I want to. Hold on. Let's do this properly. Normal. Yeah. Just want to show that I had it. It was kind of a mistake. I clicked on this just a moment ago. The idea is to click on it and then read it, like sort of, so it's time boxed. Sort of start the clock once I started reading it. Reading it's part of the problem, comprehending the problem and solving it. The amount of time it takes to do that. That's significant. So. Minimum genetic mutation. A gene string can be represented by an 8-character long string with choices from A, C, G, and T. Suppose we need to investigate a mutation from a gene string start to a gene string end. Suppose we need to investigate a mutation from a gene string start to a gene string end, where one mutation is defined as one single character changed in one single character changed in the gene string. For example, AACCGGTT, AACCGGTA is one mutation. Okay. There's also a gene bank that records all the valid gene mutations. The gene must be in bank to make it a valid gene string. Interesting. Given the 2 gene strings start and end in the gene bank, return the minimum number of mutations needed to mutate from start to end. If there is no such mutation, return -1. Note that the starting point is assumed to be valid, so it might not be included in the bank. Okay, so this is an interesting question. I think this kind of makes me think of a graph problem, or a depth first search kind of a question. Okay. Starting point is assumed to be valid, so it might not be included in the bank. Okay, sure. Start, end, bank. So you could change T to A. You could change I guess this one to that one, and then finally the end is here. There's something that's changed inside here, I guess. Was it the T and the A? Change the T, the A to the T to the A, and the C turns into an A. Okay, so first you go A. You can do either. No. You have to do it this way. Yeah, you go T to A and then C to A, and then you have what you want at the end. So the end always has to be in the bank, right? I mean, necessarily. Yeah, I can't really. It kind of goes without saying. This one, output 3. -1 if you can't get there. The number of mutations needed to mutate from start to end. This is a really interesting question. This kind of seems like a graph question, and really just like a shortest path question on the graph. But pretty much it's you would probably throw the starting point into the bank if it's not there already. But effectively, the graph could be every string in the bank. We'll just add the start string if that doesn't exist in the bank. Every string in the bank, and make an undirected graph. You have excuse me, an edge from one node to another if you can mutate one character to get from the string represented by sort of node A and node B would have a an edge if the string represented by A could be mutated to the string represented by B by one character change. That's pretty much, you could build that graph. I'm not sure how long that would take, how efficient that would be. You could build that graph, and then you want to know what's the shortest path from, if there even is a path, shortest path from the starting point to the ending point in that graph. Yeah, this could be translated to a graph problem, I think, relatively easily. Now, one question is, do you actually even need to build the graph? You may not need to, because if a depth first search can get you the shortest path, then you don't even need to create the graph, not necessarily. Although I think it's easier if you create the graph, actually, because you need a neighbor set. Yeah, how long are these strings, by the way? Okay, there's a most, start length, end length, 8 characters. Okay, that's not too bad. The bank only has at most 10. Okay, so this is like a pretty easy question in terms of like the constraints. Yeah, the graph is really small, only has 10 nodes in it. Yeah, I mean, question would be, just thinking here, the question would be, I think it's easier to build the graph first and process the graph, building the neighbor sets. How do you find the shortest path, though? That's a question. I mean, there's finding any path, but you want the shortest path. I want to say that you can do that using a form of dynamic programming, where basically you find the shortest path from every node to that ending point, and sort of the inductive step would be, if you have every other point except the starting point, you would know the shortest path. Then of the neighbors, you can take the shortest path computed. Could do it that way. Could even go so far as to number. Like, you could even go so far as to abstract this so far away that you could just basically give every node a number. Yeah, that's interesting. That's really interesting. So, okay, let's try this. We're gonna do it that way. We're gonna do a vector of vectors for the we're gonna do a vector of vector. We're gonna abstract this away into strictly a graph problem, and it'll look like the following. All right, so we'll say neighbors. Vector of vectors of ints. We're going to translate basically each string. We're going to translate that to an integer, which is going to be the its position in the bank. Yeah. I want to say just int nodes equals bank that size. Just thinking how to do this exactly. We'll just do a quick determine whether the starting string is in the bank or not. If it is, don't do anything extra, anything more. Otherwise, append a, I don't actually want, well, yeah, I guess this is fine. Use a new, yeah, we're gonna use a new extra node during our graph creation. So we'll just do a quick const auto s in bank, and we'll say if s equals, we'll do boolean, s equals start, check equals true. Alright, so now we have that check. So we do that, perform that check first. Alright, so our neighbors, the way we want to set this up is we're gonna perform, I want to say we could build the neighbor set first, and then I think the algorithm is really straightforward once you've built the neighbor set. I think that's the way to do it. Yeah, so build the neighbor set, which is a sort of a translation of the problem to a graph. The way we're going to do this is int I equals 0, I is less than bank.size plus I. Don't necessarily need to know the number of nodes, and the neighbor set we could put here. Hopefully this makes sense what I'm trying to do. I kind of have like a vague idea of what I'm trying to do. I guess we could do a round robin, because there aren't that many other strings. I'm not actually sure. Determining the neighbors. I think just thinking how I want to do this. I'm thinking for each of the neighbors, if you could do 4x8, change each character, try the 4 different possibilities for each character, and see if those are in the bank. Dump the bank strings into a set, an unordered set. And then you also probably want to match, you probably also want an unordered map of the string back to its index, because I want to build this neighbor set using indices, integers. Try to keep things simple. The problem with that though is it's like a lot of extra work just to, how are we doing on time? 15 minutes already. It's a lot of extra work to just kind of translate this to a graph. Also just to determine the neighbor set as well. I mean, hmm. Also, it's looking for the shortest path, not the longest path. I have to keep that in mind too. I mean, you know, hmm. Sorry, I'm also just thinking how to do the shortest path as well. I think it's Dijkstra's algorithm. I think it's a dynamic programming. Yeah, the way I was thinking about doing it was actually using a depth first search and just keeping a set of like nodes that we've already visited. Yeah, it's kind of it's very much like a Dijkstra's algorithm kind of a thing. I don't know. Anyway, so what are we doing? I'll figure that out next, but I kind of don't like it. But there is a way to do this. It's awkward. Yeah, I don't love this, but it's okay. Possibilities, and then we want the unordered set. And we want the unordered map. I don't really, like I said, don't love this. That's I'll just call it string to index. So string to index of bank of I is going to be equal to I, and we'll also say if not check. So we kind of want increase the number of nodes that we consider, and also add the start to the possibilities because it's not going to be covered here. String to index, we'll also say string to index of nodes is going to be nodes of start. It's going to be, so if you have 11 nodes, your largest index is 10. You have add one more to 12. It's always going to be -1. String index to start, possibilities. We're going to cover the neighbors shortly. Say string index of bank of I equals I. Possibilities. Insert. I almost want to make this like a pointer. Okay. Can't quite make this a reference. I'm not sure if that'll work properly. Yeah. So we have our string to index. We have our possibilities, and we'll sort out our neighbors shortly. I think we both need both these data structures to do this. So now we can say, actually you don't even need the possibilities anymore, because this map, the key, maybe it's, yeah, the keys are not in unordered set, so it's better to actually do it this way. Never mind. I'll explain what. Well, never mind. We're fine. No, you don't need this possibility set anymore. I'll explain that shortly. So, yeah. You don't really need this anymore, do you? Either. So now we're going to go through the neighbor set. And we're going to say string we'll call it string to index. Oh, that's awkward. All right. Do bank of I. We'll run the same routine if check is true. Sorry, I realize this is getting kind of funky, kind of wonky. Okay. So what we want to do is, for each character, we're going to replace the character in the string, and we're going to check if that string is in the string to index, if that count is non-zero, and if it is, then we're going to create. Okay, hopefully we're reconnected. Something happened, we got knocked off. So the bases, you're going to have A, C, G, T, right? And I think that should be fine, this vector. Vector of characters, bases. We're going to be const. Yeah, that's fine. And we're going to loop through each character in the bases, and we're going to say let, so temp, so we'll say character temp equals S of J, or just, yeah, or current. And we're going to say S of J equals C, and then say if string to index of S, after we've modified it, dot count, or yeah, excuse me, dot count of S is non-zero, Then we're going to take our neighbors of I and add at the end, append. We're going to append string to index of S. Quite involved. And then finally at the end, we'll say, all right, we could skip one character. I don't think it's worth it. I was going to add another if statement that if C is not equal to current, I guess it matters. I don't know. It's only one. It really shouldn't matter that much. No, it does matter actually. We don't want things looping back to themselves. That's a pretty subtle thing. It's probably better to do it this way then. Okay, and then now, after all of that, we could take S of J and set it back to the current, return it back to the state that it was in. So this is going to give us our neighbor set. Build neighbor set by build ancillary data structures or helper data structures. Swapping by considering one string at a time. And you know what we can do actually? We can copy the bank and just copy it and append to the bank this start and just keep all the if S is start, determine whether the starting string is in the bank or not. If it is, if it's not, add it to the bank. Just keep things simple. I think it's just going to make things more complicated if I try to work around that. I forget to check. We don't really need the nodes either. We can just do bank.size. And okay. Neighbors of I dot append. Oh, we need to make that size. Empty vectors. Yeah, don't bother with that part. Okay. Swapping each of the possible bases. Checking whether result exists. Each character one at a time with any of the possible bases and checking whether the result exists in the bank. If the result does, there must be a connection between the two. And by the way, the neighbor set, it's symmetric, so when you go from A to B, you'll discover that A can connect to B, and then when you look at B, you'll discover that B connects to A. So we don't need to do it sort of in one shot. As we kind of go through all of them, we'll sort of get all of the directions. So that's all well and good. So that'll build a neighbor set. Now we want to process the neighbor set. Kind of a lot of work, I think, just to get this to look like a graphing problem. Interesting. So how are we doing on time? Kind of a lot of time. It's 30 minutes just to do that. Yeah, it's interesting. So now I guess I want to run a recursive sort of memoization type of thing. So we'll say standard vector of int result is going to be bank.size at max or int max, and we're going to say auto DFS, and we'll say DFS turn result of 1 of 0, right, or of start, which actually would be interesting. That's the starting point. Okay. -1. Okay. I think in any case, the starting point is set. So if it's false, it'll be set here. If it's true, it'll be set before it's set to true. I want to say something like this. So we'll say DFS from the starting point and to the target point as well. Also -1. That has to be. This is kind of a given. This target point. This needs to be in the bank. Otherwise, it's impossible. Edge case. Right. If it's not even in the bank, the end, then obviously you'll never reach it. So you have this target point. Int, we'll say current and target, and then auto F. And this is, what does this return? I don't think it returns anything. I think it's just void. Okay, so we have this neighbor set 2. And we're going to say excuse me, base case, if res of current is not equal to int max, return that. Right, this is a kind of memoization. Basically means that we've already visited that node and determined what it should be. We'll say if current equals target, so if you're looking at the target, then you return 0. And also you're going to set result target equals 0, I guess. Not sure if that really matters. Don't have to do that. So now, say for yeah, I guess you return 0 over here as well, so you don't have any neighbors to go to. I think if you don't have any neighbors, you return -1. You can't reach. I want to say something like, if you don't have any neighbors to go to, then that means don't have any neighbors to go to. I don't think this is correct, this algorithm that I'm about to write. I don't even think it's the correct algorithm. I have to look up the shortest path algorithm. I'm about to write my own, but I don't think it's correct. If you don't have any neighbors to go to, then you can't reach the target, can you? Yeah, so I think you actually keep that as int max. Yeah, so if you're, so we're gonna say is if you can't reach the target, then we'll say it's int max. Well, I return a -1, otherwise return ret. It's a little confusing. No, that's not how I want to do it. That doesn't make sense. Because then we could end up in infinite loops if we do this kind of thing. I want to say just -1. And just return ret. Yeah, we'll handle. We'll figure that out. Let's say. Okay, let's process the neighbors. So let's say call f on new current's going to be n, and the target is not going to change, and this could be just constants in reference. And f is not going to change. And what we want to do is int ret equals int max, we'll say. And we're going to say, I guess we'll start off at, well, let's do -1, I don't know. We'll do int max, right? We'll do int max. And we're going to say int val is going to be recursively search see, that's kind of a problem, isn't it? We need a way to figure out whether or not we've already visited a particular node. I think this is wrong. I think I'm doing this wrong. I think I do need to use one of the shortest path algorithms. I don't think a simple depth first search or binary breadth first search is going to cut it. You could alternatively do a breadth first search. I mean, that works too, like a level order kind of traversal. That'll give you the shortest path. I don't really like doing that though. Kind of dislike that. Really tempted to do a level order traversal. You just need to keep track of the nodes you've already visited. I'm trying to do this without using a visited set. I want to say I want to say something like the. No, that's really funky. Because you can find a path, but it's not necessarily the shortest path. Yeah, I don't know. Let's use a visited set. Let's do that. Let's use a visited set. So we just do a unordered set. Just trying to avoid doing that. Just trying to avoid that. Yeah, okay, that's fine. I don't know if this is going to even be correct though. It's kind of part of the problem. So yeah, to int red equals max for a moment. And then we're going to say if visited of current and this is going to return an integer. I want to say something like if we've already visited, yeah, then we'll take the int max. Okay. So we have this value of f, and we want to say if val is less than ret, set ret equal to val, right? By the way, we're going to insert this, so we visited it. Yeah, we check the value first before we check whether or not we visited. And go through all the neighbors and their shortest paths and take the smallest one. Now the problem is you could be in a situation where you want to do something like this. Say if ret is not equal to int max. I think we'll do it this way. If it's not equal to int max, then we're going to set it equal to plus plus, right? And then return ret. And we're also going to say result of current equals ret. So yeah, it's going to be the minimum path of all the possibilities plus one, and you're going to return ret. And then over down here, if we just say, yeah, just do int ret equals this. This is really wonky, kind of wonky. I don't know how I feel about this. So this is int max, so you couldn't find a path. Then you're going to return -1, otherwise return ret. Yeah, I don't know. I don't like this at all. I don't like how they did this. S equals start. Yeah, I don't know. This is like a lot of thinking, a lot of work just to do something that's kind of simple, or should be kind of simple. It's not append, it's pushback. I'm remembering now. Excuse me. Where's this? 39? Oh. Fair enough. Neighbors. Yeah, not append, pushback. Visited. Of course. And lots of compilation errors. 103. Boy, oh boy. It's a lot of code, too. Something that's kind of simple. Target visited. Current target visited. Yeah. Oh, okay. Neat. I mean, I don't know. Maybe we're right. I'm tempted to try this without testing multiple cases. So this is going to be start, end is the next one, and the back looks like this. Start, end, and the back looks like this. Okay. Wow, how are we doing? 50 minutes, whoa. Alright, looks like we're correct so far, but we haven't tried any really hard test cases. Let's try one where the start point is not in there. Let's try that. Let's try one where I have some degenerate cases. Oh, the length is always going to be 8. Okay. Banks. The bank could be nothing in there. Let's try that. Bank is empty. What does that look like? Start and end. Bank consist of only the characters. And let's try one where there's no path to the target. So even though starting point's there and the ending point's there, ending point is here, and the starting point, one character difference is here. And we want to say that there's actually no path to this ending. Do AA, D, I don't know, yeah. Could do A, D, and what's that, 5, I don't know, 8, 6, 1, 2, 3, 4, 5, 6. Alright, 1, 2, 3, 4, 5, 6, yeah. Could try all these cases, see what happens. Valid test case. Okay. Oh, not D, G. How did we do? Okay, 8 milliseconds this time though. Now we want one more test case here, which is, one more test case, which is like, like a graph with like 10 different ways to get there. So we'll do like A, B, G, T, A, C, A, B, C, D, G, H, I, J, K, L, M, N, P, Q, R, S, T, U, V. Yeah, A, C, G, T, A, C, G, T. Something colorful. And we'll say we want 4 hops to get to, I don't know, ACGT, and it's going to be TGCA, something like that, right? So this won't be in the bank to begin with. We'll say this can go, we're going to make 2 different paths to get there, one of it which is longer than the other, right? ACG, TA, right, we're going to go 2 different spots. 1, 2. This one we're going to modify A to T, and this one we're going to modify C to G. And then we're going to have 2 separate paths going. There's going to take 1 extra step for this. So yeah, we'll start there. So this one, as I said, it's going to be 4 hops. So 1 to this one, 2 to this one, and this is, we're going to go straight there, right? We're going to do 4 hops straight there. C is going to become G. G is going to become C, and then A is going to become T. We're going to put that at the end. Or T, G, C, A, yeah, A at the end. And then, so that's 1, 2, 3, 4 hops. Now this one should take 5 hops. It's not going to go directly there. Modify G first, so A, G, G, T. And then I guess we'll do 2 extra mutations. So A, G, G, T, 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 C, G, T, G, and then we can modify this A to a T. Modify it back to an A, or yeah, actually modify this G. What do we want? G. Yeah, this goes to a T, and then yeah, basically we'll go to the same thing except this A. This T will go back to an A at some point. So T, G, C. Whoa. And then an A, and then this should go to the ACG, TT, GCA, yeah, okay, something like this. So how many of these are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 of these. All right, so this is kind of like just cutting it here. Let's see what happens when we do this test case. A little nervous about this one. I'm a little nervous about this one. Okay, it worked. Alright, I think we should go for it. I don't know. I mean, I've probably made a mistake somewhere. I want to say this depth first search approach doesn't necessarily work. There's probably a way to make it not work. I want to run the test cases to see. There's a good chance this is not correct. I'm a little, I don't know. I'll just say I don't know. It's probably, oh, there we go. Got there. 0 milliseconds. Nice. Alright, fair enough. So that took a while. Almost an hour. Yeah, I mean, the shortest path depth first search was kind of awkward. I was trying to avoid using a visited set, but I think you kind of need to do some kind of a visited set, and I think you need to do some kind of a visited set. You need to do some kind of a visited set Otherwise, your step first search isn't going to work properly. You do need to handle the int max properly. It's very similar to Dijkstra's. Not exactly Dijkstra's, but it's similar. Trying to think what else to say here. Wondering if we just happened to pass all the test cases, that if there were larger test cases, if this would fail in some cases. I don't actually know. Really kind of awkward how much time it took to convert this to a graph problem. I think it really simplified the logic though, by considering these just as ints. Just a simple graph problem, shortest path in a graph. Like this code is basically reusable every time you see this problem or a similar problem. The only issue is that it may not be correct. And like I said, part of the problem is this trying to not use this visited set. I think it's probably easier to do a breadth first search for this kind of a problem. Yeah, level order traversal. It's a lot simpler, the logic. The way this operates now, you do a depth first search, so you kind of drill down some path to the center, and what's going to happen is you're going to iterate through sort of all the neighbors. You're going to sort of process a full subtree before you go to the next subtree. I think in every case it's fine. You never revisit a node, which is interesting. Also significant to check whether or not you've already sort of registered a value there or not, because you won't visit it again. It means basically it's queued up at some point to be operated on. So at some point it'll be registered. But if you had already registered and it had been visited, you'll still get the value even though you visited it again. I think this is a kind of critical thing here to do this properly. Also, the target is always 0. So you always just get 1 plus 0. If that's like if you're right there, right next to it. Yeah, I mean, I think this is right. It's just, I don't know, it took me a while to code it up. I'm kind of nervous that maybe it missed something or something's wrong. Again, an hour is kind of bad. I did spend like half of an hour trying to just turn this into a graphing problem, and then the other half of an hour I was like uncertain about my depth first search traversal for the to find the shortest path. Some of these algorithms you kind of just memorize after a while, I think. I mean, I could have done this pretty quickly if I was just trying to think of a way I could do without a visited set. I don't know. I don't really know how. I think it's kind of wonky without a visited set. Yeah, even with a level order traversal, it's still pretty wonky. The level order traversal, by the way, you would probably go not from current, but you would go from the target to current, and you would just at each level you would add, you know, at that particular node you would just set that value to a like you just increment each level, all the nodes in that level would get the same number. And also you don't add nodes twice. Yeah, so if you've already visited, you skip. Yeah, you'd want to. Yeah, level order traversal is actually linear in the number of nodes. So is this, I think. You would want to assign them all, the first, so starting from the target, actually, you assign the target 0, and then all of its neighbors would get a 1. And the deal is all of those neighbors would have neighbors that are nodes you already have queued up. So as soon as you even consider something to be as soon as you consider something to be a neighbor, you add it to the visited list, so it won't be added again by any other considerations. Just do it that way. I think that's the simplest thing. And then level or traversal, you just keep at each level as you kind of progress outwards. You just keep adding, labeling each node with an increasing value. And then once everything's labeled, then and everything is default to int max. And so then you just take your starting point, and if your starting point is at max, then return a -1 because you weren't able to reach. Also, the level order traversal is better for like an infinitely sized graph, because the depth first search could just like traverse off on a path infinitely that never reaches the node you're looking for. Whereas a level order traversal is effectively you can kind of shape your graph in a way where it's like either a sphere or a what do you want to call that? Almost like if you can imagine like a circle, you could kind of rearrange the nodes like a circle. So each level is just like a larger circle, radius circle, and so you're guaranteed to eventually reach your target, even in an infinite sized map. It may take a while, but you'll get there. At that point, you might be better off actually creating like 2 circles, and then when they meet, I don't know if that's better actually. Yeah, I guess that is better. Yeah, you'd have a lot less nodes that you'd have to go through because the circles would be smaller. All right, there's sort of like a branching factor at each level. But anyway, that's just sort of abstract considerations. So yeah, I mean, okay, we did it. Simple enough. I don't really like it, I guess. Kind of for some obvious reason. Like it took me forever. It took over an hour, and that was also, not only did that take forever, but it was also it took over an hour, and it was also like a lot of work to translate this to a graph problem. Just a lot of things, and yeah, quite a bit of memory that I ended up using. I used more memory. I mean, you could do this too. You don't need to. This is a little bit faster, I think. Use a little bit less memory. I think it works, right? Yeah, slightly less memory because we're copying the bank. I kind of prefer to copy it though. Keep it simple. But yeah, so I mean, updating the bank a little bit to make sure that our string is in there, handling an edge case, doing some work to convert the problem to a graph problem, build a neighbor set, and then just perform a depth first search, shortest path, recursive algorithm. You also can do, as I said, level order traversal is probably better here, which you can do. I think you kind of need to use a visited set though for both of those algorithms. That's hard, kind of hard to do it otherwise. Yeah, I mean, it's simple enough. Simple enough. Okay. All right. Well, thank you all for watching. You do need to be careful also with this part. The int max that you get, you don't want to add 1 to int max. So that's kind of why we have this. If it's not in max, then we know it's we can add a 1 to it. You maybe could do less than in max is probably better. Yeah, in some cases, in theory, your path could actually be in max in size, which that would be awkward. So assuming that your path couldn't actually be in max in size, then we can use in max as like a placeholder for never being able to reach. So yeah. So yeah, again, thank you all for watching. Talk to you soon. Have a good rest of your day. And oh yeah, sorry, I was kind of saying less than in max is what I was saying here. Sorry, I didn't realize I had full screen already. All right, let me go. Thank you all for watching. Talk to you soon. Have a good rest of your day. If you like this stuff, don't forget to subscribe. Yeah, I'm not sure what else to say here. Have a good, yeah, take care. Take care.